Hello and welcome to the Profile Builder tutorial. Let's first navigate to the Step 1 panel. Load the event parameter file using the Load File button, and the name of the file will be displayed in the Parameter File field. An example file is included with this application. The total events in the file is shown in the Events in the File field. If the loaded parameter file is an extended parameter file from HyperExtract 2 software, click the radio button. File is the extended parameter file from HX 2.x. If the Preserve Features Selection Logics is deselected, the table in Step 3 panel will revert to its default selections upon loading a new file. If this option is selected, the feature selections of the table in Step 3 panel will remain when a new file is loaded. Events or Biphasic option is specifically for biphasic events extracted using the HyperExtract 2 software. The status indicator indicates whether the application is busy or not. Yellow means busy and green means free. The progress percentage shows the progress of computations. Now let's navigate to the Step 2 panel. In here, you can activate the parallel computing capabilities, which is a necessary requirement to build the Analyte profile. Before doing so, it is recommended to check whether parallel computing is turned on. You can do that by clicking the Parallel Status button. Right now, it says Active. If it says Not Active, click Initiate Parallels and the parallel computing will be activated. To shut down parallel computing, click Shut Down Parallels. You can also change the number of workers to be active. By default, it uses the maximum available number of workers. If you want to use a different number, deselect the Use Default Workers radio button and input the number of workers to be used under the Workers to Use field. Total workers active are displayed in the Active Workers field. Now let's navigate to the Step 3 panel. This allows you to select the features of interest to be used to build the Analyte profile. The selection or deselection fields also automatically update the Total Features field. Select All and Deselect All options allow you to select all the features or deselect all the features. The parameter name of the table is populated from the column names of the parameter file. Thus, please ensure that each column has a name that can be used to populate the table here. We are going to select 4 random features to build the profile. The Export Feature Selection button is used to export the feature selection of the table. This will be placed in the results folder that gets generated when the parameter file is loaded. The Import Feature Selection is used to import a feature selection file. Now let's navigate to the Step 4 panel. These options are to create contour maps. We ask users to refer to the color mapping tutorial for more details about these fields. The default inputs are robust and works for most systems. If there are more than one distinct population and you need to cluster the distribution, select a clustering method using the Cluster Method drop-down menu. There is a total of 6 options. Afterwards, set the target clusters using the Target Cluster field. The number of neighbors only gets active when dbScan option is chosen. The biphasic pulse selection becomes active if the Events or Biphasic option is selected. This allows the user to select both pulses, conductive pulse or the resistive pulse of the biphasic pulse to build the profile. For this file, we will keep the Events or Biphasic to selected and Cluster Method to none. The Levels tab allows you to set the total contours. If contouring is done based on population spanning, select the population span based contouring option. By default, this is set to 95%, meaning the outermost contour will engulf a minimum of 95% of the data points. If you want to normalize the features, select a method of interest using the Normalization Method drop-down menu. Once you are satisfied with the settings, click the Build Profile button. Please note that the operation time depends on the computer resources and file size. Once the profile is built, the features used to build the profile will appear in the Features text area. During the profile building, the application builds all possible bivariate plots. For example, if 13 features are chosen in the table, this results in 169 plots in a 13 by 13 feature matrix. In other words, if n features are chosen, the result will be an n by n feature matrix. Now let's navigate to the View Maps tab, which is Step 5. On the right-hand side, there are 4 tabs: Inner Contour Threshold Profiles, Outer Contour Threshold Profiles, Non-Contour Profiles, and Radial from Histograms. The inner contour threshold profiles are built using the data points inside the innermost contour. The outer contour threshold profiles uses data points inside the outermost contour. Non-contour profiles uses all data points of the plot. We will revisit the radial from histogram a little later. Let's click the Display Inner Profiles button. This creates a host of plots in the Matrix Profile tab and Radial Profile tab. If there are more than one cluster, enter the maps of the cluster to view using the View Cluster field. If Mark Diagonal is selected, red squares along diagonal appear. The diagonal corresponds to the identity plots where the same feature is plotted against itself. The polygon feature for which the map to be generated is dictated through the Polygon Feature drop-down menu. Information about polygon features can also be found in the Function Help tab. If we navigate to the Radial Profile tab, we see a host of options. Radial plots are created for each column of the feature matrix. The feature column is entered using the Select Feature field. The data can be normalized and expressed in log counts using the Normalize and Log Counts options. If Show All Radial Plots option is selected, radial plots corresponding to all the feature columns are displayed. For End features, this will be in plots. If Pop-up Plot option is created, the radial plot is plot externally. Since radial maps require positive values, if there are negative values, the program shifts values used to create the radial plot such that the minimum value is 0. The value by which the data was shifted is displayed in the Shift field. Now let's navigate to the Radial from Histogram tab. This is plotted using the histogram of each feature. The binning rule to construct the histogram can be selected using the binning rule drop-down menu. The application then takes the X value corresponding to the maximum Y value of each histogram to construct the radial plot. The data can be normalized and expressed in log counts using the Normalize and Log Counts options. If Pop-up Plot option is selected, the radial plot is plot externally. Since radial maps require positive values, if there are negative values, the program shifts values used to create the radial plot such that the minimum value is 0. The value by which the data was shifted is displayed in the Shift field. The binary map panel is critical to build the 2D binary map, which is also called the QR-like map. The threshold method defines the threshold to be used to convert the feature matrix of a chosen polygon feature into the 2D binary map. There are 6 options. Apart from the feature mean option, all other options take all the cell values of the feature matrix to build the threshold. For example, if mean is chosen, then it takes the mean of all cells of the feature matrix to compute the threshold. Any cell that is below this threshold is set to 0 and to 1 otherwise. This converts the feature matrix into a binary matrix which is plotted as the 2D binary map. If the feature mean option is chosen, then mean of each column of the feature matrix is computed separately. These thresholds are then used to compare the values in each column of the feature matrix and construct the 2D binary map. If auto thresholding is deselect, the threshold can be set manually using the threshold value field. You can also choose a feature from the feature matrix to set the threshold. This can be done by selecting the select feature for thresholding and entering the row and column value of the feature using feature index 1 and feature index 2 respectively. The value of that cell then becomes the threshold to construct the 2D binary map. Since there are 2 plot types, namely matrix plots and radial plots, the panels below allow you to change their appearances. The color matrix fields take a 3-digit input ranging from 0 to 1 and correspond to the red, green, and blue color components of the target color. Other options in Radial Plot Styling panel allow you to set the line width, grid options, grid opacity, grid line width, grid style, and font size. Under the Matrix Plot Styling panel, you set the font size, tick spacing, tick angle and plot title of the matrix profiles. The plot titles take the standard MATLAB input form. The display cell values become enabled when Pop-up Plots option is selected. The pop-up plots create the embedded figures as separate figures that can be later customized. If Display Cell Values option is selected, this enables cell text color and cell font size options. You can save and load these preferences using the Save Plot Preference and Load Plot Preference buttons. Now let's go back to the main tab and navigate to Step 6 panel. This allows you to export the data in the feature matrix. You can select the map type, polygon feature type, contour type, and cluster to export. If you want to export all map types, select Export All Map Data option. If you want to export all feature types, select Export All Feature Types option. If you want to export all contour types, select Export All Contour Data option. If you want to export all clusters, select Export All Cluster Data option. If you want to export all of the above, select Export Everything. Afterward, click Export Map Data and the corresponding data will be available in Excel sheets. The files are created separately corresponding to the 2D color and 2D binary maps for each cluster. Inside each file, information regarding the feature types can be found. These files can be used to reconstruct the 2D color and binary maps. Now let's navigate to Step 7 panel. This panel allows you to create more extensive reports. The cluster polygon data creates two Excel files. One for the innermost contour data and the other for the outermost contour data. These are similar to what we saw in panel 6 but show the data before any thresholding is performed. If you click Generate Report, it creates an extensive Word report containing all plots and matrices. It is a time-consuming exercise. We recommend selecting Delete Images after report generation and reduce numerical decimals to 3 places options. The images to be placed in the Word report are deleted after the report is generated with the first option, and the second option limits the output to 3 decimals. Now let's navigate to the Similarity Comparison tab. This allows you to create similarity matrices. The inputs for this are the files generated in Step 6 using Map Data option. We are going to load 2 example files corresponding to inner contour of an analyte that are included with this application. The similarity threshold dictates similarity level of features. It's an input from 0 to 1 with 1 being identical. When Analyze is clicked, 2 figures are created. The first figure shows features that satisfy the similarity threshold. In this case, events that are 90% similar are shown since the similarity threshold is set to 0.9. In the figure 2, the similar features are replotted in the original feature space. Since the original file has 47 features, figure 2 replots figure 1 in the 47 feature space. The appearance of the figures can be changed using options shown here. This brings the tutorial to an end. Thanks for watching.